Welcome to Ask and Learn.
In this problem, again, we're going to be doing things symbolically. So it says writing the first and second law relations and simplifying, obtain the reversible work relation for a steady flow system that exchanges heat with the surrounding medium at a temperature at T naught at a rate of Q naught dot, as well as a thermal reservoir at TR at the rate of QR dot. And again, we want to, by simplifying it, they mean to get rid of Q naught dot. So again, let me maybe just draw a little sketch or something here, just use as a reference. So we have, something like this, and then we have some work coming out, and we have some flow coming in, and then we have heat transfer. Some again, heat transfer is positive. Let's see here. Which way did I put positive? I think I put positive as in, and then some other heat transfer from the surroundings. So again, basically there's two sort, here. We don't know, this may be in or out, and this may be in or out. But we're going to eliminate this guy. So this would be W dot, and this would be Q dot R and Q dot not. So again, it's kind of like we have some flow into here. It's like a turbine, but we also have some heat transfer. Um, anyway, so it's a so again, heat in. We're going to take heat in and work out as positives here. Again, we have energy flow in equals energy flow out. And rate of entropy generation is the energy flow out minus the energy flow in. So we have, they didn't tell us how many inlets and outlets we have, but so I just made a sum out of them. So we have the rate of work out is the summation of all of the energy flow in from the enthalpy, from the velocity of the fluid, and then any gravitational potential. And again, this is really, we're worried more about changes here. And then we have the minus the rate of energy flow out. Again, the enthalpy flow out, the kinetic energy flow out, and the potential energy flow out. Again, so if there were, changes in the elevation of these, in the inlets and the exits, so like in a dam or something, that would be somewhere where you'd obviously have a lot of potential energy as the water flowed, maybe down through the turbines in the dam. And then we have the the rate of heat transfer, and this would be positive in. Now for the entropy generation, again, we have the flow of entropy out minus the flow of entropy in, and then the rate of, I think I forgot some dots here, the rate of entropy flow from the heat transfer over these, across these temperatures here. Now, they want us to eliminate Q naught. Okay, well, we can do that. Basically, multiply this equation by T naught, solve for Q naught, plug it in here, do some simplifying, and we get this lengthy expression. And this is the work that we're getting out. And we can see that, again, it is the, we have the, again, this is like the exergy flow in, exergy flow out. And then yeah, you can look at these in terms of exergies. You can also see that, we have some of this T naught terms basically because we have basically coming from when we solve for Q naught here. So you can kind of think of these as in terms of exergies. Is one way to think about it. There's lots of ways you can think about it. It's depending on how, what makes sense for you and what makes more physical sense and logical sense. I I more like to think about that these entropies take away from what we get out of here, right? Um, so what we have then is, or they basically will hamper things. Um, if everything was isentropic, right, then all of these terms would cancel with all of those terms. That's not necessarily the case. Um, and then we have our entropy, rate of entropy generation here, and then the kind of the I guess you'd call this kind of the reduced power that we're getting from the heat, because this is the normal stuff, right? Um, that we had from, let's see here, we had from this term here, right? Let's see here, is that, yeah, right. So I'm wondering why, okay, so how did that wind up being, let's see here, and okay, we multiply through by T naught, so we get the T naught from here, um, R, let's see here, Q naught, move that over there. Why is this term, I'm wondering why this term is negative here. I'm wondering if I messed this up. So let's see if we can figure this out. So we got Q naught, let me actually just do some math here. Q naught dot equals, let's see, we're multiplying through by T naught, so we get, and then move this over to the other side, or change the sign on everything, so we get Q naught, so T naught minus T naught S dot gen, right? And so then plus, this is the inlet stuff, well, that's T naught times the inlet stuff, minus T naught times the exit stuff. And then what winds up being here is, let's see here, we're going to change the sign here. Oops. We're going to change the sign, and we're going to, so that comes over here. So this winds up again being minus Q dot R over T naught over TR, right? I think that's what we got. Make sure our signs are right. Move this over to here. Yeah, no, I messed up the signs here. If you move this over to here and move this over to here, then you get minus this. But yeah, this is a minus. This is a plus. Minus, plus. And then this winds up being a minus here. So then we put that in to here. And yeah, this should be a positive. I'm sure that should be a positive term, likewise here. And check my math on this, but if you plug this into here, right, then you get the minus gen, and then you get this minus term here, right? So it's this, and then we get the subtract off the inlet entropy stuff and add in the exit, so minus plus. So yeah, this should be positive. I'm wondering about over here. Did we have a neg? Yeah, it was negative over. Maybe I'll have to redo this problem. Because I'm thinking that something's weird here, because this, I think this should be a positive term here. Likewise, because, yeah, yeah, this should be positive. I don't know why I was messing that up, but again, it's we got to keep the signs correct. So I have to redo this problem. Oh, right. Anyway, that should be a positive. I'm pretty positive. Again, heat transfer, this is work out, so this was out stuff. So that equals in stuff, and then this is also out stuff, so we moved on the other side. And then this is in stuff, and this is in stuff. Yeah. So, yeah, something, unless, did I write? No. Yeah, these things are because out, um, because these are in, this is in, positive in, so it should be, yeah. Yeah, I think that should be a positive sign, which means this should be a positive sign too. Anyway, we can then say that the reversible work, the rate of reversible work that's done is this work when the rate of entropy generation is 0. And so again, we get this lengthy expression here. So we can see how the difference here, if we wanted to figure out well, the difference between here and here, if we wanted to figure out an efficiency, right, second law efficiency, we can see that, we get a lot of the same like terms, but really we have this this term here, right, the entropy generation. And, if we spread these, if we separate these out, you can see that, we get minus basically these terms here, right, divided by these terms here is 1. So we get 1 minus this divided by this. So again, that's, kind of, again, with using the exergy business, we can figure out what, what that was in terms of exergies if we want to think about it that way.